So we're looking at the second part of the statistics course here. So this is the second test. We're looking at the standard distribution and we're looking at the linear correlations here. So we'll just get started into the first question. So it says here, a mathematical test for 300 students were normally distributed. If the mean was 65% and the standard deviation was 5%, draw and label the graph on the of the situation. So basically what you want to do with this one here is you just draw up a graph of standard distribution. It's worth 3 marks. You're going to make sure that you label each part of it. So we've got the mean of 65 and a standard distribution of 5. So standard deviation of 5. So you just got to make sure that each of the intervals, so of course just 1 minus the mean minus the standard deviation here, the mean minus 2 standard deviations, and mean minus 3 standard deviations, and so on. This one's the plus on this side here. Make sure when it says label, make sure you put in the percentage as well, and just make sure you label your graph as well, so maths test results. So that's how to gain the full 3 marks of that, and just make sure you label your units as well, so it's the mark percentage just down here. The next one says determine the percentage of students who scored between 60 and 70, and as this one lies on the intervals here, we don't necessarily need to use the calculator for this one, as we're allowed to use the 68% rule, the 95% rule, and so on. So we're allowed to use the rules here, and because these ones lie on the intervals, we can just see that it's going to be 38 plus 38%, which is going to equal 68% of students who are going to score between 60 and 70% for the test. The next part is who scored greater than 70%. So again, go to the 70% line and you can see all of these percents here. So it's going to be 13.5, 2.35 and 0.15 all added together, because they're the students that have scored more than 70%. So you add all of those together and you get a result of 16%. Now I want to know the number of students, so you've got to convert the 16% to a probability, which is 0.16 times the 300 students that did the test, and you'll get a result of 48 students. The next pass is the number of students that failed, which the pass mark was 55%. So you have to look at everyone who scored lower than 55% here. So what's the probability of that? Again, if we just have a look at the result up here, you go to 55% and you can see that it's 2.35 and 0.15 added together, which gives you a result of 2.5%. So again, that is probability times the 300 students, and you get a result of 7.5 students failed. Now, of course, you can't get 0.5 of a student failing, so we kind of just rough it up and roughly 8 students failed. And the number of students who were awarded full marks, well, we can see that full marks obviously would be 100%, and having a look at this result here, the highest interval here is only 80%. So if you went another 4 intervals up to 100%, you know, the number's going to be very, very low, and the percentage is goes back to about 9 decimal points before you get a significant figure. So really, there's no students that were awarded full marks in this one here. The second question is, we've got 160 students with a mean of 100 and a standard deviation of 15, and they want to know what percentage of students scored more than 120 points. So you can see already that you're going to get in intervals which these values aren't going to lie on. So we've got a mean of 100 and a standard deviation of 115. So the first interval will be 115. So in this one here, we don't have a nice number that's lying on the interval. So this is where we have to use a calculator and use the NCD. And with using the NCD, basically you just make we want to know more than 120. So that becomes our lower number. So our lower is 120. Our upper is can be any number, which is just not going to affect the digits. So we've done a 1 with 99 zeros. We've also got the standard deviation of 15 and the mean of 100. So you put all of this into your calculator and you're going to find the percentage of students who scored 100 more than 120 is only 9.2%. Oh, sorry, 9.12%. How many students was this? So basically, it's got to convert this back down to a probability, which was just move the decimal divided by 100. So you move the decimal point 2 back, which just becomes 0.0912 times the 160 students, and you'll get a result of 14.59 students score more than 120. Again, because you can't really have 0.59 of students, we kind of just round up to 15 students scored more than 120. Many students achieve scores within the 10 points of the mean. So basically, if you had a mean of 100, we want to know what the 10 points in between that was. Well, the 10 points in between the mean was going to be 90, so 10 points on this side, which was 90, and then 10 points on this side, which is 110. So you've got your lower of 90 and your upper of 110. So you put that back into the calculator using the NCD function, and you'll find that 49.5% of the students scored within 10 points of the mean. But how many students is that actually? Well, you times that by the 160 students we've got here, so back into the probability, and you'll find that 79.2 students, which is, again, I would roughly this one here, given that the 0.2 of a student actually lied within that, I would say that's more or less going to be within there, so roughly about 80 students, which is fine. Next question is, we have got, what would the minimum score be that a student would need to achieve to be accepted in the school that only takes the top 15%? So this one here, we're not using NCD anymore, because they've given us the area, and the area is, we want to be in the top 15% here of the final score. So to be in that top 15%, we've got to score this value here, which is unknown. We don't quite know what this value is, so that's what we're going to find out. So we're not using the NCD, we're using the inverse norm in this function here. So there's two ways to do it. If you got your tail to the left, you got to grab this area here, because you can see that the tail is over here. So if we have a tail to the left, we want to make sure that the area is 85%. So it's the 100 minus that 15%. So that's 85% of the area there. Or if you turn your tail to the right, which both of these are correct, is you have 0.15 area if you have your tail to the right. Again, just put in your standard deviation and your mean, and you'll find that the score roughly that students need to get in the top 15% is 115.6, which roughly is 116 to score in the top 15%. And then the next part here is we're moving on to the looking at a scatter plot. So basically they've given us a number of data points here, which is looking at a sunflower which grows due to water restrictions, being very careful of the water. So she's monitoring how much liters of water she puts on the sunflower, but as a result she wants to know the number of petals on those flowers, how much water she's putting onto them. So here they've given us a bunch of data points, and just a few things you've got to make sure of when you draw up a scatter plot. First is to have your title, so we're just looking at the petals versus the liters of water. It doesn't have to be that exactly, but as long as it gets roughly something like that, that will be fine. Have your y-axis title, have your x-axis title, so petals, liters of water. Now, what I would do up here as well is, you could also put here number of petals, so it's a bit more clear. I've got the P up here as well, and the L. Don't use X and Y, because the X and Y now actually have meaning, like X is the liters of water, whereas Y is the petals. So because these have meaning, we don't just use the X and Y anymore, I would use the P and L. With this one here, then what you do is basically, once you've got that drawn up, draw an appropriate scale. So this one here, just move up by intervals of 10, this one on the petals, moving up in intervals of 20. So you just got to make sure what the maximum and what the minimum is you're working with on the data set. So you can see the lowest here is 19 and the upper is 173 for the petals. So you got to make sure that your data goes roughly up to about 173 or 180. And then again with the liters runs from 8 to 96. So you're going to make sure that the x-axis supports that and is able to go up to that amount. So what we do at this point here is basically you just grab your data point. So this here is one data point. So if she gives 73 liters of water to the petal, to the plant, it will grow. This one grew 109 petals. So that's one piece of data there. So you find 73 on the axis here, which is around about there, and you go up to 109, which is roughly sitting about there. Now this, it doesn't have to be perfect, but get it as close as you can, and to ensure that your line of best fit is going to be appropriate. So you just find your next one would be 93 and 110, so 93 liters of water, which is roughly about here, and 110, which is exactly on this line across here. So there's the next data point. So each one of these here is one data point that we're putting into the graph. Once that's done, that should be finished. The line of best fit, we'll talk about that in a moment, because that's not part of the question just yet. From this point here, you need to calculate your strength of correlation. So again, once you've drawn it up, you go into it and you just find the R and R squared value. Now the R, really what that tells us is just whether it's a positive or negative. So we don't need to worry too much about this, just apart from what the number is in front. So also what the sign is. Now there's no negative sign here, so obviously it's going to be a positive. So this one here has a line of best fit, which is in the positive direction. The R squared value now of this as well, this is what tells us the strength of the correlation. So the strength of the correlation here is 0.757. Now that one there is in the line of a strong correlation, but it is on the borderline of a moderate as well. So I would probably call this one a moderate to strong positive correlation here. The next part is we've got write the equation of the least squared regression line, which is just the line of best fit, and then sketch it on your graph. So you'll find that in the calculator as well, just above the R and R squared value. Now I've used, instead of using y equals the ax plus b, I've got here the y was the petals. So if you look up here, y was the petals and the x was the liters. So I inserted that in there, so you got the petals equals 1.27 liters of water plus 19.3. And it just says sketch that on your graph. So the line of best fit, just try to get as many data points above as you can below as well, and kind of try to get in the middle as possible. Once that one's done, then it says you're not allowed to water any plants. How many petals would the sunflower expected to have? Well, if you're not allowed to water it, you're not going to have any liters of water. So that L becomes a 0, and you just solve it from there. So it becomes petals equal 1.27 times 0 plus 19.3. Of course, this just becomes 0, because any number times 0 would be 0, and then you just get 19.3 petals. The next part here, is this valid answer? Well, to be honest, you just got to think logically about this. It's probably not a valid answer, because if you don't water the plant, then the plant will most likely die, and it won't get any petals because it's not going to grow. So if the plant's not got any water, it's not going to grow. So essentially, it's not really a valid answer, to be honest. The next one says, if the sunflower had 56 petals, how much water would you expect to be on the plant? So this is where we need to use a little bit of algebra here in rearrangement of the formula. So the unknown here, we know how many petals it has. It's got 56, but we don't know the amount of or the liters of water. So what we need to do here is just rearrange the equation. So the first thing you want to get rid of is the plus 19.3, if you want to get the L on its own. So you're minus 19.3 from both sides. That cancels out the right hand side, which means that we get left with 36.7 on the left hand side. And basically what we've got here is 1.27 times the liters left. Divide that by 1.27 both sides, and then you get a result of the liters is equal to 28.7 liters of water. So roughly you're going to need around about 30 liters of water. So you're just going to make it logical. You're not going to measure out 0.9. So I would say just roughly 30 liters of water. Next part is we suspect there's an incorrect measurement in the data. So you want to find that data point. Now if there's any, basically we're just looking for any outliers here. Now the outlier we can see here is this point up here, which is well away from the data. If this one's well away, we can see it's not even close to all the other data points. This one, basically looking for outliers, is kind of done visually on a scatter plot. So we can see that this one here is pretty away from the data. So we can call that one there an outlier, which is this data point of 60 and 173. So that's that data point there. So when you've got it, just communicate that one. It appears to be an outlier because it's well away from the regression line. So you just go back to your data, remove it from your data points, and recalculate it. So again, the regression line is still positive. That's what we care about there. And the regression line now you can see is actually turned really strong. So it's become from 0.7 to 0.966, which is a very strong correlation now. So it says, how strong is it? Well, it's a very strong correlation as a result of removing the outlier. The last question says, do you think that the new equation of the line could be used for extrapolation? Well, the new equation of the line is the petals are equal to 1.22 times the liters plus 16.6. So you can see it's actually changed slightly. And the new line of best fit is can be used for making predictions, as we do have a strong correlation here. So you would say because there's a strong correlation, it is possible to make predictions. However, because it is an extrapolation, there's always a sense of unreliability because you can't predict into the future of what's going to happen. So it may not necessarily happen what we think will happen off the extrapolation. So there's always a sense of unreliability. So you've got to make sure you talk about that. And as well, when you think logically about it, if you water a plant too much, you give it too much water, you're going to drown the plant, and then it's probably going to die or not grow as many petals. So you just got to think logically about it and express that in your answer as well. While you can make an extrapolation because it is strong, it doesn't necessarily mean that will happen in the results. Hope that's helped.